In December 1970, the Soviet Union landed a spacecraft on Venus. It was sealed in titanium, engineered for a world hotter than an oven under 90 times Earth's pressure. It lasted 23 minutes. Their toughest lander managed 127. Probe dropped into Jupiter survived 58 before the planet tore it apart. None of these were malfunctions. The places we sent them are built, by physics alone, to destroy anything that arrives, and those are only the surfaces. Between them lies a vacuum that boils the fluid from your body in seconds, soaked in radiation that shreds DNA. Across distances so vast, a call for help can take hours to answer. You were handed a tidy diagram of friendly coloured marbles and told this was home. It is not. It is worse than you think. If you enjoy journeys that change how you see reality, I would really appreciate it if you hit that like button and subscribe. It helps more than you know and keeps stories like this one coming. Now, let's begin. Every child who has ever attended a science class has seen the same picture. 8 planets lined up in a neat row, spaced evenly apart, each one a colourful marble floating in clean darkness. Mercury sits close to the Sun. Venus glows a pleasant yellow. Earth shines blue and green. Mars looks rusty and adventurous. Jupiter is enormous but friendly. Saturn wears its rings like a crown. Uranus and Neptune hover in calm pastel blues at the far end of the line. That image is the single most successful lie in science education. It is not wrong because the planets are out of order. It is not wrong because the colours are inaccurate. It is wrong because it makes you feel something about the solar system that has no connection to physical reality. It makes you feel that this place is navigable, orderly, almost welcoming. The diagram implies that these worlds exist as a kind of cosmic neighbourhood, close enough to visit, distinct enough to appreciate, arranged with a logic that suggests design. Every poster, every textbook, every animated documentary you have ever watched reinforces this emotional architecture, and the emotion it builds is comfort. The comfort is a lie. The solar system is not a neighbourhood. It is a collection of lethal environments separated by incomprehensible emptiness, held together by gravity around a thermonuclear explosion 1,300,000 times the volume of Earth. Virtually every surface in this system will kill a human being within minutes. Most will do it within seconds. The one world where you can stand outside and breathe is not evidence that the system is hospitable. It is the single anomaly in a regime of overwhelming hostility. And the reason you do not feel that hostility when you think about the solar system is that you were introduced to it through a diagram that made death look decorative. Let us begin with the world closest to the Sun. Mercury orbits at an average distance of roughly 58 million kilometers from the solar surface. That sounds far. It is not. In solar system terms, Mercury is practically inside the furnace. The planet has almost no atmosphere. What exists is so thin that scientists classify it as an exosphere rather than a true atmospheric envelope. There is no weather. There is no wind in any meaningful sense. There is nothing between the surface and the vacuum of space, except a few stray atoms of sodium, hydrogen, and helium that drift away almost as fast as they appear. This means the surface has no thermal regulation whatsoever. On the day side, temperatures climb above 430 degrees Celsius. That is hot enough to melt zinc, hot enough to melt tin, hot enough to soften lead into a sluggish metallic liquid. The rocks on Mercury's sunlit hemisphere glow with heat that would destroy most industrial equipment within minutes. Then the planet rotates. Night falls, and because there is no atmosphere to retain any of that thermal energy, the temperature plummets to approximately minus 180 degrees Celsius. The swing between day and night exceeds 600 degrees. No material humans have ever manufactured for long-duration spaceflight is designed to endure that kind of thermal cycling on repeat. The stress alone would fracture most alloys within a handful of rotations. Mercury's surface is cratered so heavily that it resembles a world frozen in permanent violence. Billions of years of impacts have left it pockmarked from pole to pole. Without an atmosphere to burn up incoming debris, every object that crosses Mercury's orbital path hits the ground at full velocity. There is no erosion to smooth the scars. There is no water to fill the basins. The damage accumulates and stays, written into the surface like a record of 4.5 billion years of bombardment that never stopped. There is no possibility of human survival on Mercury's surface. Not temporarily, not with technology. The combination of extreme heat, extreme cold, hard vacuum, and direct solar radiation bombardment makes it one of the most immediately lethal surfaces in the inner solar system. You cannot stand on it. You cannot shelter on it without building a machine specifically engineered to die slightly slower than a human being would. And yet Mercury is not the worst. Not even close. Venus is worse. Venus is almost exactly the same size as Earth. It has roughly the same mass, roughly the same density, roughly the same surface gravity. In diagrams, it often appears as Earth's twin, a sibling world that looks like it should be comfortable. Some older textbooks even speculated that Venus might harbour tropical forests beneath its cloud layer. Science fiction writers imagined jungles, oceans, civilizations. The name itself comes from the Roman goddess of love and beauty. The confirmed reality is one of the most violent environments ever measured by a spacecraft. The surface temperature of Venus is approximately 465 degrees Celsius. Not in some locations, not during the daytime, everywhere, all the time. The planet's thick carbon dioxide atmosphere creates a runaway greenhouse effect so extreme that the surface temperature barely varies between the equator and the poles, between day and night, between lowlands and highlands. The entire world is a uniform furnace, hotter than most commercial pizza ovens, hotter than the maximum setting of most industrial kilns. If you placed a block of lead on the Venusian surface, it would soften, deform, and pool into a metallic puddle. 465 degrees Celsius is not a temperature that allows for the existence of complex machinery, let alone biological tissue. The atmospheric pressure is 92 times that of Earth at sea level. Standing on the surface of Venus would feel equivalent to being submerged, approximately 900 meters beneath Earth's ocean. The pressure alone would crush an unprotected human body instantly. Even hardened deep-sea submersibles are not designed to endure 92 atmospheres for extended periods. The atmosphere of Venus is not air, it is a weapon. According to NASA, the surface atmospheric density is approximately 65 kilograms per cubic meter, compared to roughly 1.2 on Earth. Walking through the Venusian atmosphere would feel less like moving through gas and more like wading through a sluggish, superheated fluid. Above the surface, the clouds are composed of sulfuric acid, not water vapor, not ice crystals, concentrated sulfuric acid droplets that would dissolve organic tissue, metals, and most structural materials on contact. These clouds extend from roughly 45 to 70 kilometers above the surface and are driven by winds that reach approximately 360 kilometers per hour at cloud top altitudes. The upper atmosphere of Venus is a corrosive hurricane. The lower atmosphere is a crushing furnace. There is no altitude at which conditions are simultaneously survivable in terms of temperature, pressure, and chemical exposure for any human being or any machine we currently know how to build for more than a few hours. The Soviet Union sent a series of landers to the surface of Venus between 1970 and 1985. The Venera program represents the only successful surface missions ever conducted on the planet. Venera 7, which landed in December 1970, was the first spacecraft to transmit data from the surface of another planet. It survived for approximately 23 minutes before succumbing to the heat and pressure. Venera 13, which landed in March 1982, holds the record for the longest surface operation at approximately 127 minutes. Both landers were engineered from the outset as machines built to endure destruction. They were sealed in titanium pressure hulls, insulated against temperatures that exceed anything found in nature on Earth's surface, hardened against chemical corrosion. They represented the absolute best that 20th century engineering could achieve against the Venusian environment. They lasted 2 hours. Think about that number. Not 2 years, not 2 months, not 2 days, 2 hours. The most advanced lander the Soviet space program could build, hardened specifically to survive Venus, was dismantled by the planet in the time it takes to watch a feature film. Not because of a malfunction, not because of a design flaw, because Venus destroyed it. The planet overwhelmed every defense the machine had. The heat degraded its electronics. The pressure crushed its seals. The atmosphere corroded its instruments. Venus does not merely kill, it dismantles. No nation has returned to the surface since. The images that Venera 13 sent back before it died remain the only colour photographs ever taken from the surface of Venus. They show a barren, orange-tinted landscape of flat rocks beneath a dense, hazy sky. The images look alien in the deepest sense of the word. Not alien like a foreign desert. Alien like a place that has no relationship to anything a human being has ever experienced directly. NASA's Da Vinci mission, currently planned for launch between 2028 and 2030, will drop a descent probe through the atmosphere. The engineers building the descent sphere describe it as being constructed like a submarine. That is the engineering vocabulary Venus demands. Not aircraft, not rovers, submarines. Because the atmosphere is that dense and that crushing, here is what makes Venus especially disturbing in the context of solar system hostility. Venus is not some distant oddity at the fringe of the system. It is Earth's closest planetary neighbour. At its nearest approach, Venus comes within approximately 38 million kilometres of Earth. In the diagram you saw in school, Venus is the marble sitting right next to ours, our twin, our sister, and its surface would kill you faster and more completely than virtually any natural environment on Earth, including the inside of an active volcano. That comparison is not rhetoric. Erupting basaltic lava on Earth emerges at roughly 1000 to 1200 degrees Celsius, far hotter than Venus in the instant it flows. But lava cools rapidly upon contact with air and rock. Within hours or days, its surface temperature drops below what Venus maintains permanently. Venus never cools. Its 465 degrees is not a peak. It is a floor sustained everywhere, at all times, with no reprieve. And at least on Earth you can walk away from the lava. On Venus, the entire surface is the hazard. There is no safe direction. If Venus is the system's furnace, Mars is its fraud. Mars is the world that most successfully exploits human optimism. It has ice caps that grow and shrink with the seasons. It has a day length of 24 hours and 37 minutes, remarkably close to Earth's. It has surface features that look like dried riverbeds carved by ancient water. Photographs from rovers show rocky landscapes that resemble the deserts of the American Southwest, with layered sedimentary rocks and dust devils spinning across open plains. Mars triggers a deep psychological response in human viewers. It looks survivable. It looks like somewhere that, with a little engineering and a lot of determination, we could learn to call home. The confirmed physical conditions tell a different story. Mars's atmosphere is less than 1% as thick as Earth's. It is composed of roughly 95% carbon dioxide. There is essentially no breathable oxygen. The atmospheric pressure at the surface averages approximately 600 pascals, compared to Earth's 101,325 pascals. That is less than 1%. The air on Mars is so thin that liquid water cannot exist on the surface. If you poured a glass of water on Mars, it would simultaneously boil and freeze, because at Martian surface pressure, the boiling point drops below the freezing point. Water does not behave like water on Mars. It behaves like a substance caught between two impossible states, flash evaporating and crystallizing at the same time. The average surface temperature is approximately minus 60 degrees Celsius. At the poles during winter, temperatures plunge below minus 120 degrees Celsius. Even at the equator during the warmest part of a summer afternoon, temperatures rarely climb above 0 degrees Celsius before crashing again at sunset. Mars is cold in a way that Earth's harshest deserts cannot approximate. The interior of Antarctica averages roughly minus 50 degrees Celsius and is considered one of the most inhospitable places on our planet. Mars is colder than Antarctica as a baseline, and it gets significantly worse from there depending on latitude, season, and time of day. But the cold is not the primary killer. The radiation is. Mars has no global magnetic field. It lost its internal dynamo billions of years ago, when its core cooled and solidified. Without a magnetic field, there is no magnetosphere. Without a magnetosphere, there is no deflection of charged particles streaming from the sun or arriving from deep space. Solar wind strikes the Martian upper atmosphere directly. Over billions of years, this bombardment stripped away most of the atmosphere Mars once had, leaving the thin remnant that exists today. And that thin remnant provides almost no radiation shielding. NASA's 2001 Mars Odyssey spacecraft measured radiation levels at Mars orbit using its Martian Radiation Experiment instrument and found ongoing exposure levels approximately 2.5 times higher than what astronauts experience aboard the International Space Station. The International Space Station orbits within Earth's magnetosphere and receives significant shielding from Earth's magnetic field. Mars has no equivalent protection. The Curiosity rover's radiation assessment detector, operating directly on the Martian surface, confirmed an average dose rate of approximately 0.7 millisieverts per day from galactic cosmic rays alone. That number does not sound dramatic until you do the math. A realistic crewed Mars mission involves approximately 180 days of transit to Mars, a surface stay of roughly 500 to 600 days while waiting for the correct orbital alignment to return, and another 180 days of transit back to Earth. Over that, approximately 960-day mission, an astronaut would accumulate roughly 1,000 millisieverts of total radiation exposure from combined transit and surface time. NASA's current career exposure guidelines place the acceptable limit at approximately 600 millisieverts for many astronaut demographics. A single Mars mission would exceed that limit. One trip, one astronaut, a career's worth of radiation and then some, absorbed in less than 3 years. And the radiation on Mars is not ordinary. Galactic cosmic rays are not like medical X-rays or airport scanners. They are heavy ions, fragments of atomic nuclei accelerated to near light speed by distant supernovae. These particles do not merely pass through tissue, they tear through it, leaving trails of molecular destruction that the body struggles to repair. The exact mechanism of their damage runs deeper than Mars alone. It is a feature of the entire space between worlds, but the consequence is already measurable. The long-term cancer risk from sustained galactic cosmic ray exposure remains one of the least understood and most feared variables in human Mars mission planning. We do not know exactly how bad it is because no human being has ever been exposed to these conditions for this long. Then there is the soil. Martian regolith contains perchlorate compounds at concentrations of roughly 0.5 to 1% by weight across wide swaths of the surface. Perchlorates are toxic to human thyroid function at trace exposure levels. They interfere with iodine uptake and can disrupt metabolic regulation. Any habitat on Mars would need to prevent even microscopic quantities of Martian dust from entering the living space, because the dust is not merely abrasive, it is chemically aggressive. Combined with the intense ultraviolet radiation that reaches the surface essentially unfiltered, the Martian surface environment is functionally self-sterilizing. Organic molecules degrade rapidly under the combination of ultraviolet flux and perchlorate chemistry, which is one reason the search for biosignatures on Mars focuses increasingly on subsurface drilling. Mars looks like a desert. It behaves like a world that has found multiple independent ways to prevent biology from surviving. Every feature that makes Mars appear familiar at first glance, the ice caps, the seasons, the rusty desert terrain, the almost Earth-like day length, is a surface-level resemblance that dissolves upon contact with confirmed physical measurements. Mars is not Earth with less air. It is a world where the air is poison, the soil is toxic, the cold is relentless, the pressure is negligible, and the radiation never stops. The rovers we send there are not exploring a future colony site. They are documenting a crime scene where habitability was murdered 4 billion years ago and never came back. Now step back and hold all three of these worlds in your mind at once. Mercury, Venus, Mars. These are not exotic outer system objects lurking in the distant dark. These are our nearest neighbours. They are the worlds that sit on either side of Earth in every classroom diagram ever printed. They are the planets whose names every child learns before the age of 10. They are the ones you can sometimes see with your naked eye, glowing steadily in the evening or morning sky, looking calm and almost inviting, and every single one of them is a confirmed, measured, documented death sentence for unprotected human life. Mercury kills with thermal extremes and vacuum. Venus kills with heat, pressure, and sulfuric acid. Mars kills with radiation, cold, and toxic chemistry. The mechanisms are different. The timelines are different. Venus would kill you in seconds. Mercury in minutes. Mars might take weeks or months as the radiation accumulates and the perchlorate dust infiltrates and the cold compounds every mechanical failure. But the result is identical across all three worlds. You die. There is no natural surface in the inner solar system, outside of Earth, where a human being could survive for a single hour without artificial life support so advanced that it essentially recreates Earth's conditions in miniature and maintains them flawlessly against an environment that is actively trying to destroy the equipment. This is the inner solar system, the so-called rocky planets, the worlds closest to the sun, the ones that fit on a single classroom poster, and among 4 worlds, only one permits human life. The other 3 are machines of destruction wearing familiar names. The diagram you saw in school was not merely oversimplified, it was emotionally misleading. It arranged these lethal worlds in a neat, colourful line and invited you to feel safe. It gave them warm names and clean colours and equal spacing. It turned a row of death chambers into a row of ornaments. And because you encountered the solar system through that diagram before you encountered any physics, the comfort arrived first. The confirmed reality came later, if it came at all. For most people, the emotional architecture of the childhood diagram is never fully replaced by measured physical data. The names still feel warm, the system still feels local, the marbles still feel like neighbours you could visit if you only had the right spaceship. They are not neighbours, they are prisoners of the same gravitational field, separated by tens of millions of kilometres of vacuum, each one locked into conditions that would obliterate human life through entirely different mechanisms. The inner solar system is not a neighbourhood. It is a lineup of worlds that each found its own independent path to being uninhabitable, and we have not yet left the region closest to the Sun. We have not yet crossed the asteroid belt into the outer system where distances multiply by factors of 5 and 10 and 30. We have not yet confronted what fills the space between these worlds, not the emptiness. The emptiness is bad enough, but what saturates that emptiness is worse. An invisible, permanent, inescapable flood of radiation and charged particles that turns every kilometre of transit into a sustained encounter with physics that has no interest in keeping you alive. The surfaces are hostile, but what lies between the surfaces might be the most dangerous environment of all. The surfaces get the attention: Venus and its furnace, Mercury and its thermal whiplash, Mars and its perchlorate dust. When people think about the dangers of the solar system, they picture places, worlds with names and textures and photographs. The hostility feels geological, grounded, something you could theoretically avoid by not landing. But the surfaces are not where the solar system is most dangerous. The surfaces are islands. The space between them is the ocean. And that ocean is trying to kill you in ways you cannot see, cannot feel, and in most cases cannot adequately shield against with any material humans currently manufacture. The moment you leave Earth's magnetic field, you enter an environment saturated with invisible violence. This violence has no weather pattern. It does not rise and fall with seasons in any cycle you can predict with confidence. It does not concentrate in one area and leave another area safe. It fills the entire volume of the solar system, from the scorched inner orbits near the Sun to the frozen emptiness beyond Neptune, at all times, without pause, without exception. And it comes from 2 entirely different sources that overlap and compound each other in ways that make long-duration human spaceflight one of the most medically uncertain endeavours ever seriously proposed. The first source is galactic cosmic rays. These are not rays in the ordinary sense. They are particles, fragments of atomic nuclei, mostly protons but also heavier ions, including the nuclei of carbon, oxygen, silicon, and iron, accelerated to velocities approaching the speed of light by astrophysical processes that occur far outside the solar system. Supernovae are the primary accelerators. When a massive star collapses and explodes, the shock wave flings matter outward at relativistic speeds. And supernovae, some of that matter enters interstellar space and eventually drifts into our solar system, arriving from every direction in a constant diffuse rain of high-energy particles. The energies involved are extraordinary. A single galactic cosmic ray proton can carry kinetic energy measured in billions of electron volts. The heaviest ions, the iron nuclei that physicists sometimes refer to as cosmic ray heavies, carry even more energy per particle and do disproportionate biological damage because of their high charge. When one of these particles strikes biological tissue, it does not leave a pinprick, it leaves a trail. The ion rips through cells along its trajectory, shattering molecular bonds, creating cascading showers of secondary particles, and depositing energy in a concentrated track that destroys DNA, proteins, and lipid membranes along its path. The body's repair mechanisms can fix many kinds of radiation damage, but the clustered, complex lesions created by heavy iron cosmic rays are qualitatively different from the damage caused by medical X-rays or even nuclear fallout. These lesions involve multiple simultaneous breaks in both strands of the DNA helix, often accompanied by chemical modifications to the surrounding bases. The repair fidelity for these lesions is lower. The probability of misrepair or failed repair is higher, and misrepair is how cancer begins. On Earth, you are almost entirely shielded from galactic cosmic rays. Two systems protect you. The first is Earth's magnetic field, the magnetosphere, which deflects the majority of incoming charged particles before they reach the upper atmosphere. The second is the atmosphere itself, which is thick enough that most particles that do enter it collide with atmospheric molecules long before reaching the ground. The combined shielding effect is enormous. The radiation dose a person receives at sea level from galactic cosmic rays is a tiny fraction of what the same person would receive standing in open interplanetary space at the same distance from the Sun. Step outside the magnetosphere, and both layers of protection vanish simultaneously. There is no magnetic deflection. There is no atmospheric absorption. You are exposed to the full, unfiltered flux of galactic cosmic rays arriving from every direction at all times, and there is currently no practical way to stop them." Unquote. This is a critical point that most popular descriptions of space radiation gloss over. Shielding against galactic cosmic rays is not simply a matter of building thicker walls. Conventional shielding materials like aluminum, which forms the hull of most spacecraft, actually make the problem worse at certain thicknesses. When a high-energy cosmic ray strikes an aluminum nucleus, it can fragment both the incoming particle and the target nucleus, producing a shower of secondary particles including neutrons, protons, pions, and lighter ions. These secondary particles spread the radiation dose over a wider volume of tissue rather than concentrating it in a single track. In some configurations, a moderately thick aluminum shield produces a higher total biological dose inside the spacecraft than no shield at all. Hydrogen-rich materials like polyethylene perform better because hydrogen nuclei are close in mass to incoming protons, which makes them more effective at absorbing kinetic energy without producing heavy secondary fragments. NASA has tested polyethylene-based shielding concepts extensively, but even optimized hydrogen-rich shielding can only reduce the galactic cosmic ray dose by roughly 25 to 35%. It cannot eliminate it. The most energetic particles, the ones carrying billions of electron volts per nucleon, will penetrate any shield of any practical thickness that a spacecraft can carry. You would need meters of material to stop them, and no crewed spacecraft can be built with walls meters thick without becoming too heavy to launch. This means that every astronaut who leaves Earth's magnetosphere begins accumulating galactic cosmic ray damage from the moment they cross the magnetopause. The accumulation is slow compared to a solar particle event, but it is constant. It does not stop during sleep. It does not stop during meals. It does not stop when the astronaut is inside the spacecraft. It is a permanent background hum of cellular destruction that continues for every second of every day spent outside the magnetosphere, and there is no technology currently in existence or in advanced development that can reduce it to zero. The second source of space radiation is the Sun itself. The Sun is not a stable, steady lamp. It is a seething, magnetically chaotic thermonuclear furnace that periodically erupts with violent releases of energy and matter. Solar flares release electromagnetic radiation across the entire spectrum. Coronal mass ejections hurl billions of tons of magnetized plasma outward through interplanetary space at speeds exceeding 3,000 kilometers per second. When these events are directed toward a region of space, occupied by a spacecraft or a planet without a magnetic field, the radiation environment changes, from dangerous to potentially lethal in a matter of hours. Solar particle events are the acute threat. While galactic cosmic rays deliver a slow, chronic dose, a major solar particle event can deliver a massive dose in a short period. The particles involved are primarily protons, accelerated to energies typically lower than galactic cosmic rays but arriving in vastly greater numbers. A strong solar particle event can increase the radiation flux in interplanetary space by orders of magnitude above the galactic cosmic ray baseline. The danger is not hypothetical. On November 11th, 2025, a significant solar particle event increased ground-level radiation on Earth by approximately 145% for roughly 2 hours, as measured by neutron monitoring stations. Earth's magnetosphere and thick atmosphere absorbed the overwhelming majority of the incoming particles. The biological effect on the surface was negligible, but in interplanetary space, without those protections, the same event would have delivered a radiation dose that poses serious health risks to any unshielded human. History provides a starker example. In August 1972, between the Apollo 16 and Apollo 17 missions, one of the most intense solar particle events of the 20th century struck the Earth-Moon system. Had astronauts been in transit to or on the surface of the Moon during that event, they would have received a radiation dose estimated to be capable of causing acute radiation sickness. Depending on their shielding conditions, the dose could have been lethal. NASA's Apollo program was extraordinarily fortunate. The event fell in the gap between two crewed missions. A matter of months separated survival from catastrophe. That is not a safety margin. That is luck. Solar particle events cannot be reliably predicted more than a few hours in advance. The Sun's magnetic activity follows an approximately 11-year cycle, and while events are more frequent near solar maximum, they can occur at any phase. The current cycle peaked in 2024 and is now declining, yet significant events continue to occur. The November 2025 event demonstrated that the Sun does not follow a neat schedule. It erupts when its magnetic field lines reconnect, and that process is governed by dynamics too complex for reliable long-range forecasting. For any crewed mission beyond the magnetosphere, solar particle events represent a rolling existential threat. Mission planners can design spacecraft with dedicated storm shelters, small, heavily shielded compartments where astronauts retreat during an event. NASA's Artemis II mission, which launched astronauts beyond the magnetosphere in 2026, incorporated exactly this kind of radiation monitoring and shelter protocol. But storm shelters add mass, they reduce habitable volume, and they require advance warning to be effective. If an event arrives faster than expected, or if its intensity exceeds the shelter's shielding capacity, the astronauts absorb the dose regardless. There is no backup. There is no second layer. Between the Sun and the human body, there is only whatever material the spacecraft provides. And for the highest energy particles, that material is often not enough. Now hold both sources of radiation in your mind simultaneously. Galactic cosmic rays, constant, penetrating, impossible to fully shield against, accumulating DNA damage every second of every day. Solar particle events, unpredictable, potentially massive, capable of delivering an acutely dangerous dose in hours. A human being in interplanetary space faces both threats at all times, and the defenses against one are largely ineffective against the other. Hydrogen-rich shielding helps with galactic cosmic rays, but is less effective against the high-flux proton storms from solar events. Heavy metal shielding helps with solar protons, but worsens the secondary particle problem for galactic cosmic rays. There is no single shielding solution that optimally addresses both threats. Every design is a compromise, and every compromise leaves gaps. This is what fills the space between planets. Not emptiness. Emptiness would be safe. What fills interplanetary space is a continuous, invisible, dual-source radiation field that has no off switch, no seasonal pause, and no technology-based solution that reduces the risk to anything close to what human beings experience on Earth's surface. The space between Mercury and Mars, between Mars and Jupiter, between Jupiter and Saturn, is saturated with this radiation at every point, at every moment. The classroom diagram shows clean, black space between the colourful planets. That clean blackness is a killing field. And then there is Jupiter. Jupiter does not merely exist within this radiation environment. Jupiter generates its own. The largest planet in the solar system possesses the most powerful magnetic field of any planet, roughly 20,000 times stronger than Earth's. This magnetic field creates a magnetosphere so vast that it extends approximately 20 million kilometers from the planet, roughly 150 times wider than Jupiter itself, and nearly 15 times the diameter of the Sun. If Jupiter's magnetosphere were visible to the naked eye from Earth, it would appear several times larger than the full moon in the night sky. Within this colossal magnetic structure, Jupiter traps and accelerates charged particles to create radiation belts that are the most intense in the solar system after the Sun itself. The particles originate from multiple sources. Some come from the solar wind, others are emitted by Jupiter's volcanic moon Io, which spews roughly 1 ton of sulfur dioxide and other volcanic material into Jupiter's magnetosphere every second. Jupiter's magnetic field captures these particles and accelerates them to enormous energies, far exceeding the energies found in Earth's Van Allen radiation belts. The result is a radiation environment around Jupiter that is lethal to both biology and electronics. The European Space Agency has stated that a human astronaut standing on the surface of Europa, Jupiter's ice-covered moon, would receive a lethal radiation dose on a timescale of hours, not days, not weeks, hours. Europa orbits within Jupiter's radiation belts, and despite being roughly 670,000 kilometers from Jupiter's cloud tops, it is bombarded continuously by high-energy electrons and ions trapped in the magnetic field. The radiation dose rate near Europa is so severe that no crewed mission to Jupiter's moons has ever been seriously proposed with current technology. The environment does not merely threaten human life, it forecloses it. Even robotic spacecraft require extraordinary engineering to survive. NASA's Europa Clipper mission, launched in October 2024 and expected to arrive at Jupiter in 2030, carries its sensitive electronics inside a specially designed radiation vault, a container built to shield transistors and processors from the accumulated bombardment. The spacecraft's total expected radiation exposure over its mission lifetime exceeds 2 million rads of total ionizing dose. To put that in context, a dose of roughly 400 to 500 rads delivered to a human body over a short period is generally lethal. Europa Clipper will absorb thousands of times that amount over the course of its mission, and it can only survive because its electronics are radiation hardened and sealed inside shielding that would be far too heavy to build at human habitat scale. Even with these precautions, the mission encountered a crisis before it left Earth. In May 2024, NASA engineers discovered that some of the radiation-hardened transistors aboard the spacecraft, metal oxide semiconductor field effect transistors, purchased from a European supplier, degraded under lower radiation doses than their specifications promised. The components were supposed to withstand the Jovian environment. Testing revealed that they would fail sooner than planned. The mission had to be redesigned to account for the weaker components, adjusting flight trajectories and operational timelines to reduce the total radiation exposure the spacecraft would accumulate. This was not a theoretical concern. It was a concrete engineering emergency caused by the sheer hostility of Jupiter's radiation belts. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, follows a highly elliptical orbit specifically designed to minimize its time inside the most intense radiation zones. Juno dips close to Jupiter's cloud tops during its closest approaches, passes through the radiation belts as quickly as possible, then swings far out into less intense regions to give its electronics time to recover. The spacecraft's principal investigator described Juno as an armored tank. That language is not metaphorical. It is engineering shorthand for a machine built to endure an environment so hostile that unprotected electronics fail within hours. Jupiter's radiation belts represent a kind of regional amplification of the solar system's overall hostility. Interplanetary space is already flooded with galactic cosmic rays and solar particle radiation. Jupiter takes that background and multiplies it by orders of magnitude within a volume of space larger than the Sun. Any mission to the Jovian system is not merely traveling through a dangerous medium to reach a destination. The destination itself is wrapped inside an additional layer of radiation so extreme that it defines the engineering limits of what human technology can endure. Jupiter is not just a planet, It is a radiation fortress, and everything within its magnetic reach is under assault. Now consider the other invisible killer that operates everywhere in the solar system. One that is so familiar it has become invisible to our intuition. Vacuum. The word vacuum suggests emptiness, absence, a benign nothingness. In reality, the vacuum of space is an active, aggressive environment that attacks biological tissue through multiple simultaneous mechanisms the instant it makes direct contact. Unprotected exposure to hard vacuum initiates a cascade of physiological failures that begins within seconds and becomes irreversible within minutes. The first effect is ebulism. At pressures below approximately 6.3 kilopascals, known as the Armstrong limit, the boiling point of water drops below human body temperature. This means that the water in exposed tissues, saliva on the tongue, moisture in the eyes, fluid in the lungs, begins to vaporize. Not because it is hot, but because the pressure is too low to keep it liquid at 37 degrees Celsius. Bubbles of water vapor form in the soft tissues, causing swelling, pain, and rapid damage to mucous membranes. This effect begins within 10 to 15 seconds of exposure. Simultaneously, the lungs cannot function. The pressure differential between the interior of the body and the surrounding vacuum would cause the lungs to attempt to expand explosively if the airway were sealed. If the airway is open, the air rushes out of the lungs in a forcible exhalation that cannot be resisted. Within 15 seconds, the oxygen partial pressure in the blood drops below the threshold required to maintain consciousness. The person loses awareness. Within 60 to 90 seconds, depending on the individual's physiology and the speed of decompression, circulatory failure begins as dissolved gases in the blood come out of solution and form bubbles that obstruct blood flow. Death in hard vacuum is not instantaneous. It is a rapid sequential shutdown that takes between 1 and 3 minutes to become irreversible. During the first 10 to 15 seconds, a person remains conscious but is already experiencing tissue damage. After 15 seconds, unconsciousness occurs. After approximately 90 seconds, the cardiovascular system fails. After several minutes, the damage is beyond any possibility of resuscitation, even if pressure is restored. This is the default state of the solar system. The overwhelming majority of the system's volume is hard vacuum. The thin atmospheric envelopes around a handful of worlds, only one of which is breathable, represent such a tiny fraction of the total volume that they barely register statistically. Between every planet and every moon, between every asteroid and every comet, between every spacecraft and every destination, there is vacuum. And vacuum does not merely represent the absence of air. It represents the presence of an environment that will kill an unprotected human being faster than the surface of Mars, faster than the cold of deep space, faster than almost any single hazard except direct immersion in extreme heat or crushing pressure. Every spacecraft ever built is a pressure vessel. It is a container designed to hold a pocket of Earth-like atmosphere against the vacuum outside. The entire history of human spaceflight is fundamentally a history of maintaining that pocket. Every seal, every gasket, every airlock mechanism, every hull panel is an engineered barrier between survival and a death that begins in seconds. A single failure in that barrier, a micrometeorite puncture, a seal degradation, a structural crack, initiates a decompression event that must be addressed immediately or the crew dies. There is no grace period measured in hours or days. The grace period is measured in seconds. The vacuum also creates secondary hazards that compound the radiation threat. In vacuum, heat transfer occurs only through radiation, not through convection or conduction with a surrounding medium. This means that thermal management in spacecraft becomes extraordinarily difficult. Surfaces facing the sun can reach temperatures above 150 degrees Celsius, while surfaces in shadow drop below -150 degrees Celsius, sometimes on the same structure at the same time. The thermal gradients stress materials, degrade seals, and create expansion differentials that must be constantly managed by active thermal control systems. A failure in thermal management can kill a crew as surely as a hull breach, just more slowly. Now assemble the complete picture. You leave Earth, you cross the magnetopause and enter interplanetary space. From this moment, you are exposed to a continuous flux of galactic cosmic rays that penetrate your spacecraft hull and deliver a slow, unshieldable dose of biologically destructive radiation to every cell in your body. You are simultaneously at risk of solar particle events that can spike the radiation environment to acutely dangerous levels with as little as a few hours of warning. Your spacecraft is a pressure vessel holding a pocket of breathable atmosphere against a vacuum that will kill you in 90 seconds if the hull is breached. The thermal environment outside swings between extremes that would destroy most unprotected materials. And if your destination is anywhere in the Jovian system, you will fly into a regional radiation environment orders of magnitude more intense than the interplanetary background, severe enough to destroy hardened electronics and lethal to human biology within hours of unshielded exposure. This is not a description of one dangerous corridor in the solar system. This is a description of all of it. Every trajectory between every world passes through this environment. There are no safe lanes. There are no calm zones where the vacuum relaxes or the cosmic rays pause. The space between planets is itself the most persistently dangerous environment in the system. The surfaces will kill you if you land without protection. The space between them will kill you while you travel, even inside a spacecraft, even with the best engineering human civilization has ever produced. The killing is slower in transit. It is quieter, but it is constant, and it is everywhere. The classroom diagram shows black space between the planets. That black space is not neutral. It is flooded with particles that shred DNA, defined by a vacuum that vaporizes tissue, stressed by thermal extremes that attack every material designed to keep human beings alive. It extends for tens of millions of kilometers in every direction, without interruption, without relief. The solar system does not merely have dangerous surfaces, it has a dangerous medium. Every journey through this system requires surviving immersion in that medium for every second of transit. The surfaces are where the danger is visible. The space between them is where the danger is permanent. And the true horror of that space has not yet been confronted, because the invisible hostility is bad enough when distances are measured in millions of kilometers. What happens when the distances multiply by factors of 10, of 30, of hundreds, and the journey time stretches from months to years to decades, is something else entirely. The killing does not stop over distance. It accumulates, and the distances in this system are so vast that accumulation itself becomes a weapon. The furnace of Venus, the radiation scouring of Mars, the invisible bombardment that fills interplanetary space, the lethal vacuum that defines the system's default state, all of it exists within a context that most people have never been forced to confront directly. That context is distance. And distance in the solar system is not merely large. It is large in a way that converts every other danger from a problem into a sentence. A problem can be solved. A problem has dimensions that engineering can address. If Venus is hot, build a machine that resists heat. If the vacuum is lethal, build a hull that holds pressure. If radiation shreds DNA, develop shielding or pharmacological countermeasures. Every hazard described so far is, at least in principle, a technical challenge that sufficiently advanced engineering might reduce or manage. That framing is what makes human spaceflight feel possible. It is what makes Mars missions feel like an ambitious but achievable next step. Distance destroys that framing. Distance does not add one more hazard to the list. It multiplies every hazard on the list by time. Radiation exposure that might be manageable over a 2-week mission becomes career-ending over a 2-year mission and potentially lethal over a 5-year mission. Equipment that can maintain hull integrity for 6 months may degrade past safety margins over 18 months. Life support systems that recycle air and water with 98% efficiency will still lose 2% per cycle, and over thousands of cycles across years of transit, those losses compound into a resource deficit that cannot be recovered in deep space. Distance is the mechanism that turns survivable dangers into unsurvivable ones. It is the multiplier that converts engineering challenges into engineering impossibilities given current technology. And the distances in the solar system are not what the diagrams suggest. Every representation of the solar system you have ever seen is a lie about distance. This is not an accusation of dishonesty. It is a statement of geometric necessity. The actual distances between planets are so disproportionate to the sizes of the planets themselves that no image, no screen, no poster, no book page can display both accurately at the same time. If you drew the planets at their correct relative sizes and placed them at their correct relative distances on a single sheet of paper, the planets would be invisible. They would be smaller than the smallest dot a printer can produce, separated by gaps wider than the paper itself. The only way to show all 8 planets in a single image is to lie about how far apart they are. Every diagram does this. Every diagram must do this. And the result is that every human being who has ever looked at a picture of the solar system has absorbed a deeply distorted sense of how much empty space separates one world from the next. Here is what the distances actually look like. The average distance from the Sun to Earth is approximately 150 million kilometers. Astronomers call this distance 1 astronomical unit. It is the baseline measurement for everything else in the system. Light covers this distance in approximately 8 minutes and 20 seconds. That means the sunlight warming your face at any given moment left the solar surface more than 8 minutes ago. You are not seeing the sun as it is now. You are seeing it as it was when the light departed. The sun could theoretically cease to exist and you would not know for over 8 minutes. Mars, at its closest approach to Earth, comes within roughly 55 million kilometers. At its farthest, when Earth and Mars are on opposite sides of the Sun, the distance stretches to approximately 400 million kilometers. The practical distance for mission planning varies depending on orbital alignment, but a realistic one-way transit to Mars using current propulsion technology requires approximately 6 to 9 months. 6 to 9 months of continuous travel through the radiation-saturated vacuum that fills every trajectory in this system, with no possibility of emergency return, no resupply, and communication delays that reach up to 22 minutes each way. A distress call sent from a Mars-bound spacecraft would take nearly a quarter of an hour to reach Earth. The response would take another quarter of an hour to travel back. By the time a crew received any answer, 44 minutes would have passed. In a decompression event, 44 minutes is not a delay, it is an obituary. Jupiter orbits at an average distance of approximately 778 million kilometers from the Sun, roughly 5.2 astronomical units. At its closest approach to Earth, the gap shrinks to approximately 588 million kilometers. At its farthest, it exceeds 960 million kilometers. Light from the Sun takes approximately 43 minutes to reach Jupiter. A radio signal from Earth to a spacecraft in Jupiter orbit takes between 33 and 54 minutes depending on orbital positions. The Juno spacecraft, traveling at speeds that required a gravitational assist from Earth to achieve, took approximately 5 years to reach Jupiter. After its launch in 2011, 5 years of transit, 5 years of accumulated radiation exposure, thermal cycling, mechanical wear, and zero possibility of repair or resupply. If any critical system had failed during that transit, the mission would simply have been lost. There is no roadside assistance between Earth and Jupiter. There is nothing between Earth and Jupiter except 600 million kilometers of irradiated vacuum. Saturn doubles the distance. It orbits at approximately 1.4 billion kilometers from the Sun, roughly 9.5 astronomical units. Light from the Sun takes approximately 1 hour and 20 minutes to reach Saturn. The Cassini spacecraft took nearly 7 years to reach Saturn after its launch in 1997, and that timeline required 4 separate gravitational assists from Venus, Earth, and Jupiter. 7 years. Consider the engineering required to build a machine that operates continuously for 7 years in hard vacuum, surviving thermal extremes, radiation bombardment, and the vibrational stresses of multiple planetary flybys, without a single hands-on repair, without a single component replacement, without anyone ever physically touching the spacecraft after it left the launch pad. Uranus sits at approximately 2.9 billion kilometers from the Sun, roughly 19 astronomical units. Neptune orbits at approximately 4.5 billion kilometers, roughly 30 astronomical units. Light from the Sun needs over 4 hours to reach Neptune. Only one spacecraft in human history has ever visited either world. Voyager 2 flew past Uranus in January 1986 and past Neptune in August 1989, more than 12 years after its launch in 1977. No spacecraft has returned to either planet since. No mission to Uranus or Neptune is currently in transit. though proposals are under study. The ice giants remain among the least explored major objects in the system, precisely because getting there requires a commitment of time and resources that pushes against the limits of what space agencies can sustain. But even Neptune does not mark the edge of the solar system. Beyond Neptune's orbit lies the Kuiper belt, a vast ring of icy bodies extending from roughly 30 astronomical units to approximately 50 astronomical units from the Sun. This region contains Pluto, Eris, and hundreds of thousands of smaller icy remnants that never accumulated into a full-sized planet. NASA's New Horizons spacecraft, which launched in January 2006 and flew past Pluto in July 2015, took 9.5 years to reach the Kuiper belt despite being the fastest spacecraft ever launched from Earth at the time. It departed Earth at approximately 58,000 kilometers per hour. Even at that speed, more than 16 times faster than a rifle bullet, the journey to Pluto consumed nearly a decade, and the Kuiper belt is still not the edge. Beyond the Kuiper belt lies a transitional region where the solar wind weakens and eventually yields to the pressure of the interstellar medium. This boundary, the heliopause, marks the outer limit of the Sun's direct influence on the surrounding plasma environment. Voyager 1 crossed the heliopause in August 2012 at a distance of approximately 121 astronomical units from the Sun. That is roughly 18 billion kilometers. The spacecraft had been traveling for 35 years to reach that point. As of mid-2026, Voyager 1 is approximately 166 astronomical units from the Sun, roughly 25 billion kilometers from Earth. A radio signal traveling at the speed of light takes approximately 23.5 hours to reach it. In November 2026, Voyager 1 is expected to pass the 1 light day threshold, meaning a command sent from Earth will take a full 24 hours to arrive, and the response will take another 24 hours to return. A complete round-trip communication requires 2 days. Voyager 1 is the farthest human-made object from Earth. It has been traveling for nearly 50 years. It moves at approximately 17 kilometers per second, or roughly 61,000 kilometers per hour, and it has not left the solar system, not even close. The Sun's gravitational influence extends to the Oort cloud, a hypothesized spherical shell of icy bodies that may extend from roughly 2,000 astronomical units to as far as 100,000 astronomical units from the Sun. Even at its current speed, Voyager 1 would need approximately 300 years to reach the inner edge of the Oort cloud, and roughly 30,000 years to pass through it entirely. To reach Proxima Centauri, the nearest star to the Sun at a distance of approximately 4.2 light-years, Voyager 1 would require approximately 73,000 years. 73,000 years. Human civilization in its entirety, from the earliest agricultural settlements to the present day, spans roughly 12,000 years. Voyager 1 would need to travel for 6 times the duration of all recorded human history to reach the nearest neighboring star, and that star is cosmically next door. The solar system is so vast that our fastest spacecraft, traveling for nearly half a century, has covered a distance that would not register as a visible movement on a map drawn at the scale of the nearest stars. This is what distance means in the solar system. Not an inconvenience, not a logistical challenge. A wall. An absolute physical wall built from the speed of light and the sheer geometric scale of the system's architecture. And this wall does not merely separate us from the stars, it separates us from the planets. It separates every world in the system from every other world by gaps so large that crossing them requires months or years of continuous exposure to every hazard this system contains. Let that compound. Every minute spent in transit is a minute spent absorbing galactic cosmic rays. Every hour is an hour during which a solar particle event could erupt without sufficient warning. Every day is a day of mechanical wear on life support systems that cannot be serviced by any external crew. Every week is a week in which the statistical probability of micrometeorite impact, seal degradation, or component failure ticks incrementally upward, and there is no shortcut. There is no faster route. The distances between planets are governed by orbital mechanics that cannot be argued with or engineered around. You can optimize trajectories. You can use gravitational assists to gain speed. You can develop more efficient propulsion systems, but you cannot change the fact that Jupiter is 5 astronomical units from the Sun, and that crossing 5 astronomical units takes years with any propulsion system that currently exists or is under serious development. Distance also severs the most fundamental lifeline any human being depends on, the ability to call for help and receive a response. On Earth, emergency communication is effectively instantaneous. A phone call connects within seconds. A distress signal reaches responders within minutes. The gap between crisis and assistance is small enough that intervention is meaningful. In low Earth orbit, communication delays are negligible. Even on the Moon, the delay is approximately 1.3 seconds each way, barely noticeable, easily workable. On a Mars mission, the delay destroys real-time interaction. At minimum, the one-way signal time is roughly 3 minutes. At maximum, it exceeds 22 minutes. A crew facing a medical emergency, a fire, a hull breach, a life support failure, cannot consult with mission control in any meaningful real-time dialogue. They send a message. They wait. They receive a response that was formulated based on information that was already 20 or more minutes old by the time it was received on Earth. By the time advice arrives, the situation aboard the spacecraft has evolved for over 40 minutes since the original report. In a fast-moving emergency, 40 minutes is not a communication delay. It is functional isolation. At Jupiter, the delay extends to nearly an hour each way. At Saturn, over an hour. At Neptune, the round-trip communication time approaches 9 hours. A crew experiencing a critical failure at Neptune would spend an entire working day alone with the problem before hearing a single word of guidance from Earth. This communication isolation does not simply make emergencies harder to manage. It redefines the psychological landscape of spaceflight. Every crew member beyond the inner solar system knows that they are, in practical terms, alone. Not alone in the poetic sense. Alone in the operational sense. The decisions they make during a crisis will determine whether they live or die, and those decisions must be made without consultation, without confirmation, without the reassuring voice of a flight controller who can see telemetry in real time and offer informed guidance. The further from Earth a crew travels, the more completely they are severed from the infrastructure of human support that defines every other dangerous profession on Earth. Firefighters have dispatch. Soldiers have command. Deep-sea divers have surface crews. Astronauts beyond Mars have a time-delayed text channel and their own judgment. Psychological research on long-duration isolation, studied in analog environments like Antarctic stations and submarine deployments, consistently identifies the same risks. Interpersonal conflict amplification, decision fatigue, an emotional withdrawal that deepens as missions lengthen. The psychological pressures compound the physical dangers. A crew that is fatigued, isolated, and increasingly strained by interpersonal friction is a crew more likely to make errors in judgment. And in an environment where a single error can breach a hull or mismanage a radiation shelter protocol, the margin between survival and catastrophe is vanishingly thin. Now turn outward past the planets and consider what fills the outer solar system. The answer is almost nothing. The outer solar system is a void of a kind that defies earthly analogies. Between the orbits of the giant planets, there are no waypoints, no rest stops, no intermediate destinations where a spacecraft could dock, resupply, or shelter. The distances between Jupiter and Saturn, between Saturn and Uranus, between Uranus and Neptune, are measured in billions of kilometers of empty space, punctuated by nothing except the occasional stray asteroid or comet nucleus. Objects so small and so widely separated that encountering one by chance is statistically negligible. The sunlight in the outer solar system fades according to the inverse square law. Double the distance from the sun, and the light intensity drops to 1/4. At Jupiter, sunlight is approximately 1/27th as intense as on Earth. At Saturn, approximately 100th. At Neptune, the sunlight is roughly 900 times weaker than on Earth's surface. Stand on Triton, Neptune's largest moon, and the sun would appear as a brilliant but tiny point in the sky, noticeably brighter than any other star but providing essentially no warmth. The surface temperature on Triton is approximately -235 degrees Celsius. That is only 38 degrees above absolute zero. At those temperatures, nitrogen, which makes up the majority of Earth's atmosphere, freezes solid. Triton's surface is covered in nitrogen ice. The landscape is so cold that the very substance we breathe as a gas on Earth lies underfoot as a frozen crust. And yet the outer solar system contains worlds that inspire more public optimism than almost any destination in the inner system. These are the moons that dominate headlines about the search for extraterrestrial life. Titan, Enceladus, Europa, already discussed for its radiation nightmare, but grouped in popular imagination with these others as a place where life might lurk beneath ice. The public narrative frames these moons as promising. Hopeful, the next frontier. The confirmed physical conditions tell a story so far from that framing that the gap between expectation and reality rivals Venus. Start with Titan, Saturn's largest moon and the only moon in the solar system with a dense atmosphere. Titan's atmosphere is roughly 1.5 times the surface pressure of Earth's, which makes it unique among all moons and gives it a superficial resemblance to a habitable world. It has weather. It has rain. It has lakes and rivers and seas that pool in basins and carve drainage channels across the landscape. The Cassini orbiter and the Huygens probe, which descended to Titan's surface in January 2005, confirmed all of this. Huygens transmitted data from the surface for approximately 72 minutes before its batteries died, revealing a landscape of rounded pebbles in an orange-tinted haze that looked eerily like a wet riverbed on Earth. The resemblance is a trap. The rain on Titan is not water. It is liquid methane. The rivers are methane. The lakes are methane and ethane. The surface temperature is approximately minus 179 degrees Celsius. At that temperature, water is not a liquid. It is a rock. Water ice on Titan behaves the way granite and basalt behave on Earth. It forms the bedrock. It forms the mountains. The geological cycle that Earth runs on water, evaporation, condensation, precipitation, erosion, Titan runs on hydrocarbons. The chemistry is alien not in a subtle way, but in a fundamental way. Every liquid process on Titan operates with molecules that are flammable on Earth, at temperatures so far below human survivability that exposed skin would suffer cryogenic burns in seconds. The atmosphere, despite its comfortable pressure, is roughly 95% nitrogen and nearly 5% methane. With no detectable free oxygen, it is unbreathable. Not unbreathable in the way Mars is unbreathable, where the issue is mainly pressure and composition. Unbreathable in the way a sealed chamber filled with inert gas is unbreathable. You would lose consciousness within seconds and die within minutes. The thick atmosphere also blocks virtually all direct sunlight. Titan's surface receives roughly 1% of the solar energy Earth's surface receives. The landscape exists in a permanent twilight, so dim that human eyes would struggle to distinguish shapes at a distance. It is a world of freezing hydrocarbon rain, falling through orange haze onto water ice bedrock in near-total darkness. The word promising does not belong anywhere in that description. Enceladus generates even more optimism, and for a more compelling reason. This tiny moon of Saturn, only roughly 500 kilometers in diameter, vents plumes of water vapor and ice particles from fractures near its south pole. The Cassini spacecraft flew through these plumes multiple times and detected water, salt, silica nanoparticles, molecular hydrogen, and simple organic molecules. The chemistry is consistent with hydrothermal activity on the floor of a subsurface ocean, the same kind of chemistry that supports ecosystems around deep-sea vents on Earth. If any world in the outer solar system harbours conditions compatible with microbial life, Enceladus is among the strongest candidates, but the surface of Enceladus is approximately minus 201 degrees Celsius. The subsurface ocean, if it is habitable, lies beneath an ice shell estimated at roughly 20 to 25 kilometers thick at the South Pole and potentially much thicker elsewhere. The plumes that Cassini sampled erupt through cracks in this ice at velocities that suggest they originate from a pressurized reservoir far below the surface. Reaching that ocean would require landing on a world with no atmosphere in the deep outer solar system where solar power is useless, and drilling through kilometers of ice harder than steel at those temperatures. The engineering required does not exist and is not under development in any funded program. Enceladus is a world where the most exciting scientific discovery in the solar system may be locked behind a barrier of ice, cold, distance, and engineering impossibility so severe that no credible mission architecture exists to breach it. The gas giants themselves offer no surface at all. Jupiter and Saturn have no solid ground. Their visible cloud layers, the colourful bands and swirling storms that dominate every photograph, are simply the top of an atmosphere that deepens and compresses continuously with altitude. Descend into Jupiter's atmosphere, and the pressure increases smoothly from near vacuum at the cloud tops to crushing intensities thousands of kilometers below. At some depth, the hydrogen atmosphere transitions from gas to liquid without a distinct boundary, and deeper still it compresses into a metallic state where hydrogen conducts electricity like a metal. There is no landing on Jupiter. There is only sinking into increasing heat, increasing pressure, and increasing darkness, until every material and every structure fails. NASA's Galileo atmospheric probe dropped into Jupiter in December 1995, transmitted data for approximately 57 minutes as it descended. It reached a depth of roughly 150 kilometers below the cloud tops before the temperature and pressure destroyed it. The probe was built to endure extreme conditions. Jupiter exceeded those conditions in under an hour. These are the worlds that populate the outer solar system. The moons that inspire headlines about alien oceans are locked beneath kilometers of ice at temperatures where metals shatter. The moons with atmospheres rain flammable hydrocarbons in permanent darkness. The giant planets have no surfaces, only atmospheres that compress into oblivion. And every single one of them exists at distances from Earth measured in billions of kilometers, reachable only after years of transit through the radiation-saturated vacuum already described. The outer solar system is not a frontier waiting to be settled. It is a collection of environments so hostile that even robotic exploration requires decade-long missions, nuclear power sources, and engineering tolerances that push the limits of human manufacturing. The most hopeful destinations in the outer system are hopeful only in the scientific sense, meaning they might teach us something about the chemistry of life. They are not hopeful in the human sense. They are not places anyone could go. They are not places anyone could survive. They are the most distant, most isolated, most hostile environments in the system, wrapped in the most optimistic language our culture can produce. And the gap between the language and the physics is the outer solar system's own version of the diagram lie. Different in form, identical in function, comfort where none is warranted. Beyond the false promise of those moons, the engineering reality of the outer solar system reasserts itself. Earth's coldest recorded temperature is approximately -89 degrees Celsius, measured at Vostok Station in Antarctica. The surface of Pluto averages approximately -230 degrees Celsius, roughly 140 degrees colder than anything on Earth. These are not temperatures that any biological process known to science can operate in. They are not temperatures that most mechanical systems are designed to endure. Lubricants solidify, metals become brittle, rubber and polymer seals lose flexibility and crack. The engineering required to operate any machine at these temperatures demands specialized materials and designs that add mass, complexity, and failure modes to every system. The outer solar system also receives almost no useful solar energy. Any spacecraft operating beyond Jupiter cannot rely on solar panels for power. The sunlight is too faint. This is why every deep outer system mission in history has been powered by radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium-238 into electricity. These generators are reliable but produce limited power, typically a few hundred watts at the start of a mission, declining over time as the plutonium decays. For comparison, a household hairdryer consumes roughly 1,500 watts. Every instrument, every heater, every communication system, every computer aboard an outer system spacecraft must operate within a power budget smaller than most household appliances, and the supply of plutonium-238 is limited. Production was halted for decades and has only recently been restarted at small scale by the United States Department of Energy. The fuel that powers exploration of the outer solar system is itself a scarce resource. The outer solar system is not merely distant, it is impoverished. It is a region of space where energy is scarce, light is faint, temperatures approach absolute zero, and the distances between objects of any interest are measured in billions of kilometers. It is the part of the solar system that the classroom diagram compresses most aggressively, squeezing Neptune and Uranus into the same visual frame as Jupiter and Saturn, when in reality, each successive planet is roughly twice as far from the Sun as the one before it. The outer system is where the true scale of the solar system reveals itself most nakedly, and what it reveals is a darkness so vast and so empty that it reduces every human capability to insignificance. Consider what it means to combine everything discussed so far into a single scenario. A crewed spacecraft leaves Earth orbit and crosses the magnetopause within hours. From this point, every crew member absorbs galactic cosmic ray damage continuously. The spacecraft is a sealed pressure vessel. A single hull breach means death within minutes. Communication with Earth degrades with every passing day. The crew carries all consumables with them. Nothing can be added. Nothing can be replaced. Every kilogram must last until the mission ends, whether that comes in months or years. If the destination is Mars, the transit takes approximately 7 months each way, with a surface stay of over a year. If the destination is Jupiter's moons, the transit alone takes 5 to 7 years. If some future mission aimed for Neptune's moon Triton, the transit would take over a decade with current technology. Throughout every day of every one of those transits, the crew is exposed to radiation they cannot fully shield against, dependent on life support systems that degrade over time, isolated from real-time communication with Earth, and surrounded by a vacuum that will kill them in seconds if the hull fails. There is no emergency extraction. There is no abort-to-Earth option beyond the first few days of any deep space mission. Once a spacecraft is on a trajectory to Mars or beyond, the laws of orbital mechanics dictate when it can return. Changing course requires fuel that was budgeted for the planned trajectory. Expending that fuel on an emergency return may mean there is not enough to slow down at the destination or to enter a return trajectory later. The crew is committed. The distances are too great and the velocities too high for improvised course changes. The physics does not negotiate. This is the solar system that the diagram never showed you. A system where the distances between worlds are so enormous that crossing them requires committing human lives to years-long immersion in a lethal environment, with no possibility of rescue, no possibility of resupply, and a communication link that degrades from real-time conversation to time-delayed correspondence to, eventually, something closer to sending letters that take days to arrive. A system where the nearest planet takes months to reach, the middle planets take years, and the outer planets take decades. A system where the distance itself is not a gap between dangers but an amplifier of every danger, stretching exposure times, compounding equipment degradation, and erasing every safety margin that short-duration missions depend on. The classroom diagram made the solar system look like a set of destinations. In reality, it is a set of traps separated by killing fields so wide that reaching any of them requires surviving years inside the field first. And the further outward you look, the worse it gets. The distances grow, the temperatures plummet, the light fades, the energy vanishes, the communication dissolves. Everything that human survival depends on — warmth, light, air, water, contact, proximity to help — diminishes with distance from the Sun in a gradient so steep that by the time you reach the outer planets, you are operating in conditions that barely qualify as compatible with the continued function of machinery, let alone the continued existence of a biological organism. The solar system is not a neighborhood with some dangerous blocks. It is a desert so vast that crossing it may be the single most dangerous sustained activity human beings have ever seriously contemplated, and we have not yet confronted the deepest implication of that fact. Because the distances and the dangers and the isolation do not merely stack alongside each other, they stack on top of each other. They compound, they interact. Every form of hostility in this system reinforces every other form, and the combined weight of that compounding hostility is what makes the solar system, as a system, far worse than any individual world or any individual hazard can convey on its own. The total is not a sum, it is a product. And the product is something that the word home was never designed to describe. You now know what the surfaces do. You know what fills the space between them. You know how far apart they are and what that distance means for anyone foolish or brave enough to try crossing it. Each of those realities is devastating on its own, but the solar system's true hostility does not live in any single category. It lives in the interaction between all of them, the compounding, the stacking, the way every danger in this system reinforces and amplifies every other danger until the total weight of the architecture becomes something no individual fact can communicate. This is where the pieces merge into a single picture. And the picture is worse than the pieces. Begin with what compounding actually means. Radiation does not wait for distance to finish causing problems before it starts its own. It operates simultaneously. A crew in transit to Mars is not first exposed to distance and then exposed to radiation. They are exposed to both at the same time, continuously, for months. The distance determines how long the radiation acts. The radiation determines how much biological damage accumulates during the time that the distance imposes. Remove either variable and the problem becomes more manageable. A high radiation environment that you can leave in hours is survivable. Most people who receive diagnostic X-rays do not develop cancer. A long-duration journey through a benign environment is exhausting but not physiologically destructive. Submarine crews deploy for months in a sealed tube but do not return with damaged chromosomes. The solar system offers neither mercy. It pairs extreme radiation with extreme duration and gives you no mechanism to reduce one without confronting the other. Vacuum compounds in the same way. The danger of vacuum is not merely that it exists, but that it exists everywhere and always. For every second of every mission beyond Earth's atmosphere, the crew lives inside a sealed vessel that must not fail. On a 2-week shuttle mission to low Earth orbit, the statistical probability of a catastrophic hull breach is extremely small. The exposure window is short. The vessel has been inspected recently. Rescue options exist. Stretch that same engineering challenge across a 2-year Mars mission and every variable degrades. Seals age. Micrometeorite impacts accumulate probabilistically. Thermal cycling stresses joints and welds through thousands of additional expansion-contraction cycles. The vessel is the same vessel, built from the same materials, but the distance has converted a manageable risk into a creeping certainty that something, somewhere in the structure, will weaken. On a mission to Jupiter's moons lasting 5 to 7 years, the engineering margins thin further. Every additional year of operation is a year during which the hull must hold. The seals must not degrade past tolerance, and every weld must remain intact against an environment that destroys any failure with lethal immediacy. Temperature compounds too. The thermal environment of deep space cycles between extremes with every rotation of the spacecraft, every change in orientation relative to the sun, every transition between sunlight and shadow. These cycles stress materials through a process called thermal fatigue. A metal panel that heats to 150 degrees Celsius on its sun-facing side and cools to minus 150 degrees on its shadow side undergoes a 300-degree swing. If that cycle repeats once every 90 minutes, as it does in low Earth orbit, the panel experiences roughly 5,700 cycles per year. Over a 7-year mission to Saturn, that same panel would endure roughly 40,000 thermal cycles. Materials that perform perfectly at cycle 1,000 may develop microfractures by cycle 30,000. And microfractures in a pressure vessel surrounded by vacuum are not cosmetic imperfections. They are incipient catastrophes. Life support compounds most insidiously of all. The systems that recycle air and water aboard a spacecraft are engineered to high efficiencies, but no recycling system achieves 100% recovery. Each cycle loses a small fraction of the total supply. On a short mission, these losses are negligible. Carry slightly more consumables than you need and the margins are comfortable. On a multi-year mission, the losses accumulate. Filters degrade and must be replaced from finite onboard stocks. Chemical reagents used in carbon dioxide scrubbing are consumed and cannot be replenished. Water purification membranes lose efficiency over thousands of hours of continuous operation. The life support system does not fail in a dramatic singular event. It erodes. It becomes fractionally less effective with each passing month, and the crew's survival margin shrinks in proportion. By the 3rd or 4th year of a deep space mission, The system that was comfortably within tolerance at launch may be operating at the outer edge of its design envelope, with no possibility of overhaul, no replacement components beyond what was carried from Earth, and no margin for the kind of unexpected demand that an emergency would create. And there is one more compounding variable that the solar system imposes on any crew that attempts to cross it. It is not a feature of space itself, like radiation or vacuum. It is a consequence of how human bodies respond to the absence of gravity, and it begins the moment the engines cut off. In microgravity, the human body begins to dismantle itself. This is not a metaphor. It is confirmed physiology measured across decades of data from the International Space Station. Without the constant downward pull of gravity, the skeleton receives no load signal. The bones respond by shedding calcium and mineral density at a rate of approximately 1 to 1.5% per month. On Earth, severe osteoporosis might reduce bone density by 1 to 2% per year. In microgravity, an astronaut can lose as much bone mass in 6 months as an elderly person loses in a decade. The bones become brittle, the risk of fracture increases, and the calcium released into the bloodstream must be filtered by the kidneys, increasing the risk of kidney stones in an environment where surgical intervention is impossible. Muscles atrophy simultaneously. Without gravitational resistance, the body reduces investment in muscle tissue it no longer needs. Leg muscles, back muscles, and the postural muscles that keep a person upright on Earth all begin to waste. Astronauts on the International Space Station exercise for roughly 2 hours every day specifically to slow this degradation, and even with that regimen, they return to Earth measurably weaker than when they left. A crew in transit to Mars for 7 months, on the surface for over a year, and in transit home for another 7 months would spend the majority of the mission in either microgravity or the reduced gravity of Mars, which is only 38% of Earth's. The cumulative muscle and bone loss over a 3-year mission has no precedent in human spaceflight data. The cardiovascular system degrades as well. In microgravity, bodily fluids shift toward the head. The heart remodels, becoming rounder and less efficient. Blood volume decreases. Upon return to gravity, astronauts frequently experience orthostatic intolerance, fainting or losing consciousness when standing, because their cardiovascular systems can no longer manage the downward pull on blood. After a multi-year deep space mission, the severity of this reconditioning is unknown because no human has ever attempted it. More recently, research on long-duration International Space Station crews has identified a condition called spaceflight-associated neuroocular syndrome, in which the redistribution of fluid toward the head increases intracranial pressure, deforming the optic nerve and altering vision. Some astronauts have returned from 6-month missions with permanently changed eyesight. The condition appears to worsen with mission duration. Its progression over a multi-year mission is unstudied because no mission of that length has ever been conducted. The immune system weakens in microgravity. International Space Station studies have documented reactivation of latent viruses in astronauts whose immune function was suppressed by the spaceflight environment. Wound healing slows. In a sealed spacecraft where every crew member shares the same air and microbial environment, an immunocompromised crew is vulnerable to cascading illness with no hospital and no evacuation. None of these effects can be fully prevented with current technology. Exercise mitigates but does not eliminate bone and muscle loss. No pharmacological intervention has been demonstrated to prevent cardiovascular remodeling or immune suppression in microgravity. Artificial gravity through spacecraft rotation has been proposed theoretically, but has never been implemented on a crewed mission beyond brief experimental tests. The engineering complexity, the structural requirements, the rotational dynamics, all remain unsolved at mission scale. This means that distance compounds the body's own degradation in exactly the same way it compounds every other hazard. A 2-week mission to the moon causes measurable but reversible physiological changes. A 6-month International Space Station mission causes significant changes that require weeks of rehabilitation. A 3-year Mars mission would cause changes whose severity and reversibility are genuinely unknown. A 5 to 7-year mission to the Jovian system would subject human bodies to cumulative microgravity exposure so far beyond any existing data that the medical outcomes are not just uncertain, they are unpredictable. The crew might arrive at their destination too physically degraded to perform the mission. They might arrive home too physiologically altered to recover fully. No one knows. The data does not exist because the distances required to generate the data are the distances that the solar system imposes on any mission to its outer reaches. The solar system does not merely irradiate you on the way to Jupiter, it also slowly dismantles your skeleton, atrophies your muscles, reshapes your heart, pressurizes your skull, suppresses your immune system, and degrades your eyesight. It does all of this simultaneously, alongside every other compounding hazard. For every day that distance forces you to remain in transit. The body is not a passive passenger. It is another system under attack, from the inside, by the absence of the one force that Earth provides, and that the rest of the system does not. Every one of these compounding effects is driven by the same underlying variable, time in the hostile environment. And time in the hostile environment is dictated by distance. The further you go, the longer you are exposed. The longer you are exposed, the more every system degrades, every risk accumulates, every margin shrinks. Distance is not a separate danger. It is the engine that converts every other danger from acute to chronic, from survivable to cumulative, from a challenge to a verdict. Now add the solar system's most chaotic variable, impact. The solar system is not a static arrangement of planets and empty space. It is a dynamic environment populated by millions of objects in independent orbits, many of which cross the paths of other objects at velocities measured in tens of kilometers per second. Asteroids, comets, and smaller debris fill the system in concentrations that vary by region but never reach zero. The inner solar system contains a population of near-Earth objects, asteroids and cometary fragments, whose orbits bring them within 1.3 astronomical units of the Sun and therefore into the vicinity of Earth's orbital path. As of recent surveys, astronomers have catalogued more than 34,000 near-Earth objects. The actual population, including objects too small to detect with current telescopes, is estimated to number in the millions. Most of these objects are small, pebbles, boulders, fragments that would burn up in Earth's atmosphere as meteors, producing nothing more than a streak of light in the night sky. But size distributions follow a power law. For every large object, there are many more smaller ones, and the smaller objects vastly outnumber the larger ones. The critical implication is that the large ones, while rare, exist. And when a large one strikes, the consequences scale with devastating nonlinearity. The Chicxulub impact approximately 66 million years ago is the most thoroughly documented example of what happens when a large solar system object intersects a planet's path. The impactor was estimated at roughly 10 to 15 kilometers in diameter, a rock the size of a small city, traveling at approximately 20 kilometers per second. It struck what is now the Yucatan Peninsula of Mexico and released energy equivalent to roughly 10 billion nuclear weapons detonated simultaneously. The impact excavated a crater more than 180 kilometers in diameter. It injected billions of tons of dust and aerosols into the atmosphere, triggering global wildfires, acid rain, and a prolonged impact winter that collapsed food chains worldwide. Approximately 75% of all species went extinct, including every non-avian dinosaur. One rock, one impact, 75% of all life erased. This was not an anomaly. It was the most recent major impact in a long series that has punctuated Earth's geological history. The late heavy bombardment, approximately 4 billion years ago, subjected the inner solar system to a barrage of impacts so intense that no surface feature from before that period survives intact on any world. The Moon's cratered face and Mercury's scarred landscape are direct records. The bombardment has not stopped. It has slowed. The population of large impactors has been depleted over billions of years, as most objects were either swept up by planets, ejected from the system, or ground down by collisions. But the population is not zero. New objects are perturbed into planet-crossing orbits by gravitational interactions with Jupiter, by the slow orbital drift caused by thermal radiation effects, and by the occasional passage of a star near the outer Oort cloud that sends fresh comets spiraling inward. The supply of potential impactors is continuously replenished. The rate is lower than 4 billion years ago. It is not zero. In 1994, comet shoemaker Levy 9 provided a spectacular demonstration of what happens when a solar system body encounters a giant planet. The comet, which had been captured into orbit around Jupiter and subsequently torn into fragments by tidal forces, struck Jupiter's atmosphere over a period of 6 days in July of that year. The largest fragment impacts produced explosions visible from Earth, generating temporary atmospheric scars larger than the diameter of Earth itself. The energy released by individual fragment strikes was estimated at millions of megatons of TNT equivalent. Had any of those fragments struck Earth instead of Jupiter, the result would have been a civilization-ending catastrophe. Closer to home, the Tunguska event of 1908 flattened roughly 2,000 square kilometers of Siberian forest, when an object estimated at 50 to 60 meters in diameter exploded in the atmosphere above the remote Tunguska River region. The blast released energy equivalent to roughly 10 to 15 megatons of TNT, hundreds of times the yield of the Hiroshima weapon. No impact crater was formed because the object disintegrated before reaching the surface, but the atmospheric shock wave destroyed 80 million trees across an area larger than many major cities. Had the object arrived 4 hours later, Earth's rotation would have placed the city of St. Petersburg under the blast zone. In February 2013, a roughly 20-meter asteroid entered Earth's atmosphere over Chelyabinsk, Russia, and exploded at an altitude of approximately 30 kilometers. The airburst released energy equivalent to roughly 500 kilotons of TNT, roughly 30 times the Hiroshima yield. The shock wave shattered windows across the city, injuring over 1,500 people, mostly from flying glass. No warning was issued. The object approached from the direction of the sun and was invisible to ground-based telescopes until it entered the atmosphere. It arrived without announcement and caused more human injuries than any confirmed asteroid event in modern recorded history. The asteroid 99942, Apophis, a roughly 370-meter wide near-Earth object, will pass within approximately 32,000 kilometers of Earth in April 2029. That distance is closer than the orbital altitude of geostationary communications satellites. Apophis will not impact Earth during that pass. Subsequent analysis has ruled out a collision for at least the next century. But the pass illustrates the tight margins involved. 32,000 kilometers is a rounding error in solar system terms. It is less than 3 Earth diameters. An object large enough to devastate a continent will pass so close to Earth that it will be visible to the naked eye, moving noticeably against the background stars in real time. The system's random violence does not always miss. This is the solar system's final compounding layer. Beneath the radiation, beneath the vacuum, beneath the thermal extremes, beneath the crushing distances, there is a constant, low probability, high consequence risk of catastrophic impact. The system is full of debris. That debris is in motion. Some of it crosses our orbit, and the history of Earth, written in the geological record, confirms that large impacts are not theoretical scenarios from a textbook. They are events that have occurred repeatedly over the life of the planet, and there is no physical mechanism that prevents them from occurring again. Now, hold the complete picture. Surfaces that kill through heat, pressure, radiation, cold, vacuum, and toxic chemistry. Interplanetary space saturated with DNA-shredding cosmic rays and unpredictable solar storms. Distances so vast that crossing them requires years of continuous exposure to every danger simultaneously. Temperatures ranging from hot enough to melt metals to cold enough to freeze the gases we breathe. Life support systems that erode with no possibility of resupply. And millions of objects in chaotic orbits, some large enough to end civilizations. This is not a list of individual dangers. This is a system. Every danger reinforces every other danger. Radiation is more lethal because distance forces long exposure. No. Distance is more dangerous because radiation and vacuum and thermal cycling degrade the equipment that must survive the journey. Equipment degradation is more threatening because the distance precludes repair or resupply. Impact risk is more terrifying because the distances between detection and arrival are measured in seconds for small objects and weeks for larger ones, leaving margins that are functionally invisible against the backdrop of orbits that span billions of kilometers. Nothing in this architecture cancels out anything else. Nothing provides relief from anything else. The system's hostilities do not alternate. They stack. And now ask yourself, why none of this feels intuitive? The answer is familiarity. You were taught the solar system before you were taught physics. You learned the names of the planets before you learned what temperature, pressure, radiation, or vacuum actually do to a human body. You absorbed the emotional shape of the solar system as a child, from posters and models and picture books, and that emotional shape was warm, orderly, and inviting. Mercury was the little one, Venus was the bright one, Mars was the red one, Jupiter was the big one, Saturn was the pretty one. Each planet had a personality, a colour, a character. They felt like places you could know, places that belonged to you. That emotional architecture was never replaced. It was supplemented. As you grew older, you learned facts about surface temperatures and atmospheric compositions. But the facts arrived late, after the feeling. They were layered on top of an existing emotional framework that said, this place is ours, this place is local, this place is home. And because the emotional framework came first, it has structural priority. It is the foundation. The facts are the furniture. You can rearrange the furniture. You cannot easily replace the foundation. This is why the solar system feels less dangerous than it is. The word Mars does not trigger fear. It triggers a faded memory of a red dot on a classroom poster, a vague sense of familiarity, maybe a flash of a rover photograph that looked like a pleasant desert. The word Jupiter evokes grandeur, not menace. Saturn evokes beauty. Even Venus, the most hostile of the inner worlds, evokes nothing more threatening than its mythological namesake in most people's minds. The names are comfortable. The names feel old and known and safe. And because the names feel safe, the places feel survivable, even though every measurement ever taken on those worlds confirms the opposite. Familiarity is the deepest layer of the solar system's deception. Not the diagrams alone, not the compressed distances alone, not the cheerful colour schemes or the tidy orbital lines. Familiarity itself, the simple, powerful, pre-rational sense that you know this place because you have heard its name since childhood. That sense of knowing creates an illusion of accessibility. It whispers that the solar system is approachable, that its worlds are destinations, that its spaces are traversable, that its dangers are manageable by creatures clever enough to name everything in it. They are not. We named Mercury 4,000 years ago. We still cannot build a machine that survives on its surface for more than a few hours. We named Venus thousands of years before that. We sent our best lander and it lasted 127 minutes. We named Mars before we knew what radiation was, and we now know that its surface would irradiate an unshielded human into cancer risk within months. We named Jupiter before we understood magnetism, and we now know that its magnetic field creates a radiation environment lethal to biology and barely survivable by hardened electronics. We named everything. We understood almost nothing. And the names stuck. The comfort stuck. The sense that these are our worlds, familiar and close and belonging to us, stuck. But they do not belong to us. We belong to Earth. One world, one thin shell of breathable air, one magnetic field, one temperature range narrow enough to keep water liquid on the surface, one radiation shield just strong enough to block the worst of the cosmic and solar bombardment. Everything that makes human life possible exists in a layer approximately 10 to 15 kilometers thick around a rocky sphere, roughly 12,700 kilometers in diameter. Below that layer, the Earth's interior is molten rock and metal at temperatures exceeding 4,000 degrees Celsius. Above that layer, the atmosphere thins rapidly until it becomes indistinguishable from the vacuum of space. The habitable zone of Earth is a film, a skin, a membrane stretched over a ball of iron and silicate, insulated from a universe that would kill its inhabitants instantly if any of the protective systems failed. And this membrane is the only place in the entire solar system where any of those protective systems exist. No other world has a breathable atmosphere. No other world has a global magnetic field strong enough to deflect galactic cosmic rays and solar particle storms. No other world has surface temperatures within the range that permits liquid water to persist in open air. No other world has atmospheric pressure sufficient to prevent your blood from boiling in the warmth of your own body. Earth is not one hospitable world among several. Earth is the single anomaly in a system that is otherwise uniformly lethal. The solar system did not produce 8 worlds and make one of them nice. It produced 8 worlds and made 7 of them, various flavors of death, plus one where a specific, improbable, finely balanced combination of conditions allows carbon-based biology to persist on the surface. The word home obscures this reality. We say the solar system is our home, and the word carries connotations of shelter, safety, belonging, comfort. But a home, in the human sense, is a place where the environment supports your existence, a place where you can breathe the air, drink the water, walk outside without dying. By that definition, the solar system is not our home. Earth is our home. The solar system is the hostile environment that surrounds our home on every side, extending outward for billions of kilometers in every direction, saturated with radiation, defined by vacuum, frozen or burning at every surface except one, and so vast that crossing it would require exposing human bodies to conditions they were never evolved to endure for durations that exceed every known safety threshold. Calling the solar system home is like calling the ocean home, because you live on one island. The island is home. The ocean is what will kill you if you step off the island without extraordinary preparation and extraordinary luck. And this ocean is wider, deeper, colder, more irradiated, and more violently indifferent to human survival than any body of water on Earth. It is an ocean that you cannot swim through because there is nothing to swim in, an ocean where the medium itself is lethal, and the distance between islands is measured in years of travel. We have sent robots to the other islands. Some survived for minutes, some survived for years, none survived permanently. Every machine we have ever sent to another world in this system has eventually been destroyed by the environment it was sent to study. Every one. Not because the machines were poorly designed, because the environments are that hostile. We build the best technology our civilization can produce, send it millions or billions of kilometers through irradiated vacuum, land it on a surface that is frozen or burning, or bathed in radiation or crushed by atmospheric pressure, and we watch it operate for as long as it can before the environment wins. And the environment always wins, not because we are careless, because the solar system is relentless. And here is the thought that most conversations about space exploration prefer to leave unspoken. The solar system's hostility is not a temporary condition that future technology will dissolve. It is structural, built into the system at the level of fundamental physics, and no engineering advancement changes the constants that define it. The distances between planets are set by gravity, orbital mechanics, and the mass of the Sun. They are not going to shrink. No propulsion technology, no matter how advanced, changes the fact that Mars orbits 1.5 astronomical units from the Sun and Jupiter orbits 5.2. Faster engines reduce transit times, but they do not eliminate them. Even the most optimistic proposals for advanced propulsion, nuclear thermal rockets, ion drives, theoretical fusion engines, still project Mars transit times measured in months, and Jupiter transit times measured in years. The speed of light imposes a hard ceiling on how fast any information or any vehicle can traverse these distances, and that ceiling guarantees that communication delays and isolation are permanent features of deep space travel, not temporary inconveniences awaiting a technological fix. The radiation environment is set by astrophysics. Galactic cosmic rays originate in supernovae that occurred millions of years ago in distant regions of the galaxy. Their flux through the solar system is governed by the Sun's magnetic activity cycle and by the galactic magnetic field. Neither of these can be engineered. Solar particle events are driven by the Sun's internal magnetic dynamics, which are chaotic, inherently unpredictable beyond short timescales, and completely beyond human influence. The radiation that saturates interplanetary space will saturate it for as long as the Sun exists and the galaxy continues producing supernovae. It is not a problem to be solved, it is a condition to be endured. The vacuum is set by the distribution of matter in the solar system. Governed by how the system formed 4.5 billion years ago, the planets accumulated nearly all available material. The spaces between them were left empty and will remain empty for the remaining lifespan of the Sun. No technology fills a vacuum across millions of kilometers of interplanetary space. The vacuum is permanent. The thermal extremes it creates are permanent. The impact risk is set by the orbital dynamics of millions of asteroids and comets, whose trajectories are perturbed by gravitational interactions that will continue for billions of years. The population of potential impactors is continuously replenished. The risk cannot be reduced to zero. It can only be monitored, object by object, generation by generation, indefinitely. This is not a pessimistic interpretation. It is a physical description. The solar system's hostility is not a frontier-era problem that will fade as civilization matures. It is an intrinsic property of the system, as fundamental as its size, as permanent as its orbital structure, as inescapable as the speed of light. Technologies will improve. Missions will become more capable. Humans may eventually walk on Mars, sample the ice of Europa, photograph the methane seas of Titan up close, but they will do all of this inside the hostile architecture, not beyond it. They will carry their atmosphere with them. They will absorb radiation they cannot fully block. They will travel for months or years through vacuum they cannot fill. They will arrive at destinations that will try to destroy them through mechanisms that no technology eliminates, only manages, temporarily, imperfectly, at enormous cost. The solar system will not become friendlier. It will not soften with time. It will not reward human persistence with gradually improving conditions, the way a harsh climate on Earth eventually yields to shelter and agriculture and infrastructure. The harshness of the solar system is not a surface that can be worn down. It is the bedrock, and the bedrock does not move. This is what worse than you think means. It does not mean that one planet is scarier than you realized. It does not mean that space is empty and cold. It does not mean that radiation is a concern for astronauts. It means that the entire system, taken as a whole, viewed as a single architecture of physical conditions, is more hostile, more empty, more violent, and more fundamentally incompatible with human existence than the familiar picture allows you to feel. The hostility is not concentrated in one region. It is distributed everywhere. It is the default. It is what every cubic kilometer of this system contains, unless you happen to be standing on the surface of one specific rocky world at one specific distance from the sun, wrapped in one specific atmosphere, shielded by one specific magnetic field, in one specific era of geological stability. The solar system is not a dangerous place that contains a safe spot. It is a lethal place that contains one miraculous exception, and the exception is so thin, so local, so dependent on a precise combination of factors that could each be disrupted by processes already present in the system: impact, solar evolution, magnetic field decay, that even the exception is not guaranteed. Earth is safe today. Earth was not safe 66 million years ago, when an asteroid ended the age of the dinosaurs. Earth will not be safe 5 billion years from now, when the sun expands into a red giant and engulfs the inner planets. The safety is temporary. The hostility is permanent. You are taught the solar system as a place of wonder, and it is wondrous. The rings of Saturn are beautiful. The storms of Jupiter are magnificent. The ice geysers of Enceladus are extraordinary. The ancient riverbeds of Mars are haunting. The system is full of phenomena that inspire awe and curiosity and the deepest kind of scientific fascination. None of that wonder changes the physics. None of that beauty makes the surfaces survivable or the distances crossable or the radiation tolerable. You can marvel at a thing that would kill you. Humans do it all the time. We marvel at volcanoes. We marvel at hurricanes. We marvel at the deep ocean. But we do not confuse marveling with belonging. We do not call the caldera of an active volcano home simply because we find it beautiful. The solar system deserves our wonder. It does not deserve our comfort. The comfort was planted by a childhood diagram, and it has persisted because no one ever formally replaced it. The names stayed warm, the colours stayed friendly, the distances stayed compressed, and the result is a civilization that speaks casually about colonizing Mars, mining asteroids, and settling the outer moons without fully confronting the physical reality that every step away from Earth is a step deeper into an environment that is trying, in every measurable physical dimension, to end you. This system is worse than you think. not because of any one danger, because of all of them, together at once, compounding across distances so vast that exposure cannot be shortened, reinforcing each other in ways that no single engineering solution can address, wrapped in a familiarity so deep that most people never pause to question whether the word home is appropriate for a place that would kill them in seconds at virtually every location except the one they are standing on right now. The solar system is not your home. Earth is your home. The solar system is the beautiful, magnificent, awe-inspiring machine of destruction that surrounds your home on every side. And the only reason you do not feel it is that you have never had to leave the one place in all of it where the machine, for the moment, for reasons of physics and luck, and 4.5 billion years of improbable stability, has not yet reached you.